I'm delighted to be giving this plenary lecture at the first virtual Goldschmidt, but at the same time, of course, very sad that we're not in Hawaii. My lecture today will focus on volcanic outgassing and magmatic volatiles at Kilauea Volcano, which is the most active volcano in the Hawaiian Islands, situated here on the Big Island. So the island of Hawaii is made of 5 juxtaposed volcanoes, and Kilauea, here on this Landsat image, has grown perched on the south flank of Mauna Loa. The summit caldera is here, and 2 rift zones extend off to the east and the southwest. Now, Kilauea is a prodigious emitter of volcanic gases, and in this image from the early 2000s, you can see plumes both from the summit here and from the East Rift Zone eruption site of the time at Pu'u'o. So why is understanding degassing important? I can give you a few reasons here. The first is for volcano monitoring. Gas flux and composition is one of the principal ways in which we develop eruption forecasts and early warning systems. Volcanic gas data can also help us to understand where magmas are stored in the crust prior to eruptions, and primitive melt volatile compositions can help us understand the nature of the mantle source. Eruptions of Kilauea and other ocean island volcanoes are the best analogue that we have in the modern day for ancient flood basalt eruptions, which have played such an important role in influencing life and shaping our environment. And last here, but not finally, Kilauea is an important source of pollutants, which impact human health and our environment. So I'm going to touch on all of these aspects during this talk. So let's start at the beginning. In 1912, a pressing question occupying volcanologists of the time was, are the vapours emitted from volcanoes smoke or gas? So Shepherd and Dodge provided the first analyses of volcanic gases at Kilauea, and this is a photo of them sampling gases in Halemaumau crater at the summit of Kilauea, and they showed that water was the principal component of the gases. Thomas Jagger, educated at Harvard and the founder of the Hawaiian Volcano Observatory, asked questions such as, are volcanic exhalations from the interior of the earth, or are they reworked surface water? So here, Thomas Jagger is taking lava samples from Halemaumau in 1917, and he also collected a series of gas samples called the J series, and identified a sequence of gases that showed conclusively through their composition that they were sourced partly from the interior. He identified water, nitrogen, CO2, sulfur and chlorine gases, although the speciation is not quite right here, and argon. Analytical methods of the day were fairly primitive spectroscopy and gas chromatography. The next breakthrough came during the 1967 summit eruption, when John Norton of the University of Hawaii was the first to use infrared spectroscopy to measure the compositions of volcanic gases. And here are some spectra acquired using a lava fountain as a source of infrared, with the cold volcanic gases passing in front of the hot source and absorbing characteristic wavelengths in the IR. So the top spectrum shows the characteristic absorptions due to, so for example, here's SO2, water and CO2, and he acquired background spectra here at the bottom to show that SO2 was present in the gas, this is the absorption signature here, but not in the background. So he showed that the composition of the volcanic gases emitted during fountaining were largely water with some CO2 and SO2. Terry Gerlach of the USGS features prominently in this story, and he recognised that Thomas Jagger's volcanic gas collections were heavily contaminated by meteoric water and air, and he set out to reconstruct them in 1980. He showed that summit eruption gases were actually very rich in CO2 relative to water, here in this column, and by calculating equilibrium temperatures thermodynamically using the equilibria between various gas pairs, he was able to reconstruct the oxygen fugacity in this column here, which lay slightly above the QFM buffer. Now, these are some very general classification diagrams that gas geochemists use to characterise the compositions of volcanic gases. On the left, nitrogen and argon present in air, and helium. Volcanoes in subduction zones are often very rich in nitrogen, and that's derived from subducting sediments. And morb gases are very rich in helium. On the right here we have carbon dioxide, water and sulfur gases. And gases from arc volcanoes are typically very rich in water, whereas gases from intraplate and rift volcanoes are rich in carbon and sulfur. Now, when we plot on Jagger's reconstructed gas analyses, we see that these have really helped to define these fields. The gases are Morb-like in terms of their helium, argon and nitrogen. I should also mention that the proportion of helium-3 in these gases is very high. This is data from Hilton et al. Showing R over RA values, that is the helium-3-4 ratio compared to air, of 13.7 to 15.9, and that's consistent with them being sourced from a lower mantle component. Now, throughout the 1980s and 90s, a clearer picture of Kilauea's plumbing system began to emerge, based on seismicity, which showed earthquakes directly beneath the summit of Kilauea and extending down to depths of 40 or 50 kilometres, and also shallowly beneath the rift zones at depths of a few kilometres. And also geodesy, which showed that the south flank of Kilauea is moving rapidly southward. These data are from Miklius in 2005, but it was Swanson et al. Who pointed out in 1976 that this large flank movement may be due to forcible intrusion of magma into the rift zones. Gravitational spreading at the edifice may also play a role. So these new data led to an understanding of the volcano's plumbing system, whereby magma ascended from depth beneath the summit and then migrated laterally along a shallow zone to erupt on the rift zones. And this is a cartoon published by Ryan in 1988. The next stage of our understanding of volatiles at Kilauea was greatly aided by discoveries brought about by dredging basaltic glasses from the Puna Ridge, led by Jackie Dixon and David Clegg. And the Puna Ridge is an extension of the East Rift Zone submarine environment here, shown on the map. Now, before I show you what they found, I need to lay out the enormous progress made in experimental petrology through the 80s and 90s, which led to the formation of volatile solubility models, upon which much of our current understanding is based. So here's just a very small selection of studies which contributed to these new models, which essentially laid out how much of a particular volatile species can be held in solution in a silicate melt under different conditions of temperature and pressure. So two examples are shown here. One is a water-rich arc dacite where sulfur and CO2 and even water degas from the magma quite deep during storage in crustal reservoirs. In contrast, for a water-poor ocean island basalt such as Kilauea, CO2 exsolves into bubbles deep again, but water and sulfur remain in solution until very low pressures during magma ascent to the surface. And degassing mostly takes place in the top 800 to 1,000 metres under magmastatic pressure. Now, the different volatile species interact with one another and lower their solubility relative to the one component system. And this plot shows the proportions of CO2 and water that can dissolve in silicate melts for different pressures. And it shows a degassing path here in red that a magma might take as it's decompressing up towards the surface and erupting, whereby most of the CO2 is lost at high pressures and then the water at much lower pressures. Now, basalts that erupt on the sea floor typically retain most of their water because the pressure of the water column, the water thickness, column H, is high enough to keep it in solution, whereas much of the CO2 has been lost by degassing. So Dixon and Clegg and others, through analyses of these glasses dredged from the sea floor, including the most primitive ever found at Kilauea, up to 15% weight MgO, provided the first evidence for Kilauea melts containing between 0.4 and 0.8 weight % of water. Now, some glasses had degassed much of their water, despite the water column, which led Dixon et al. 1991 to propose a vertical convective mixing regime beneath the summit, which allowed magmas to rise, partially degas, sink back and mix with volatile rich magmas before being injected into the rift and erupted. In 1985, Gerlach and Graeber published their model of degassing at Kilauea in Nature. They proposed, based on the available gas data from the summit eruptions, the J-series data, and the petrological evidence uncovered by Dixon and Clegg, that magma rises beneath the summit, degasses much of its CO2, which emerges as a CO2-rich plume that degasses in a diffuse way on the caldera floor, Then magma migrates laterally during rift zone eruptions and degasses most of its sulfur and water very close to the surface. The prediction was that a summit eruption, gas plumes here would be more CO2 rich than for rift eruption plumes. Now, there are immediately plenty of opportunities to test this emerging model. The long-lived Pu'uoa eruption began in 1983, located on the East Rift zone, here about 35 kilometres from the summit, creating a large lava flow field which extended all the way to the ocean. Here's an aerial view of the summit caldera as it looked early in the Pu'uoa eruption and the Pu'uoa eruption site. Now, a time series of SO2 fluxes were established by the Hawaiian Volcano Observatory USGS team led by Jeff Sutton and Tamar Elias, which showed that SO2 fluxes were typically a few hundred tonnes per day at the summit and heavily influenced by rainfall events which scrubbed the SO2. And on the East Rift Zone eruption site, where magma was decompressed right up to down to atmospheric pressure, the SO2 flux was much higher, on the order of a few thousand tonnes per day. Now, I had the enormous honour to hold a Mendenhall Fellowship in 2003 to 2005, during which time I carried out FTIR measurements of volcanic gases at Kilauea, both at the eruption site at Pu'uoa, shown in this image in 2005, and at the summit, where there was no eruption taking place at the time. And these measurements worked on the principles of Beer's law, here shown on the left, and I used hot lamps and infrared lamps as infrared sources. Now, average gas compositions derived from regressions of the data, shown here, some examples, of a large number of measurements showed that summit gases during a period of no summit eruption were very rich in CO2, had a carbon-sulfur ratio here at the average about 17.7. In contrast, at the East Rift Zone, volcanic gases were very carbon poor, with an average carbon-sulfur ratio of about 0.6, consistent with Gerlach and Graeber's model. Now, a real challenge in volcanic gas geochemistry, and that is really true today as well, is measurement of CO2 fluxes. And yet, if most of the magma rising beneath the summit degasses most of its CO2 there, then the CO2 flux at the summit has potential to be a proxy for magma supply rate. So this is a really important measurement to make. Now, measurements of CO2 flux were carried out in the 2000s using UV spectroscopy to derive the SO2 flux, and electrochemical sensors and infrared sensors to measure the ratio between carbon and sulfur in the plume. And these instruments were mounted downwind on a road vehicle, and the plume was sampled. And the plume was under the influence of the trade winds, which typically blew from the northeast. And two striking features emerged from the data. The first is that the sources of sulfur and carbon in the summit caldera are different spatially. So carbon, CO2, was derived from a diffuse area of the caldera floor to the east and southeast of the Halemaumau pit crater, whereas sulfur, SO2, was derived from discrete and localized vents around the edge of the Halemaumau pit crater. The second feature of the data was that the CO2 flux was high, averaging around 8,500 tonnes per day, compared to the SO2 flux, which is much lower, the order of a few hundred tonnes per day. Now, another facet of the story are measurements of carbon isotopic composition of the volcanic gases, which showed that the delta-13 carbon composition gases at the East Rift was much lighter, these are shown in blue, than at the summit. So this is -9 to -7 per mil, compared to -4 to -3 per mil at the summit. And this is consistent with the heavier carbon isotope, carbon-13, partitioning into the gas phase and being lost from the magma at the summit, and then the remaining relatively light carbon degassing from the magma at the rift zone eruption site. And this is illustrated by a magma degassing model here, presented by Gerlach in 1990. Now, I should say the isotopic fractionation factor of carbon during degassing remains poorly understood. Here are some estimates from the literature. Now, in 2008 came a new opportunity to characterise the gases emitted during a summit eruption, the first since the early 20th century, when a new lava lake appeared in the Halemaumau crater at the summit of Kilauea. Now, SO2 fluxes from the summit immediately jumped up to several thousand tonnes per day, and CO2 fluxes preceding the eruption were high, up to 20,000 tonnes per day, as presented by Poland et al. Now, we had the opportunity to measure the composition of volcanic gases during the lava lake activity in 2008 using electrochemical sensor packages, and found that the gases from Halemaumau were actually carbon depleted compared to Jagger's 1917 J-series analyses. So here's Jagger's carbon-sulfur ratio measured in the early 20th century, and here is the ratio that we measured. And our gases were actually more similar in composition to the East Rift Zone eruption gases, which were carbon depleted. And these measurements showed that magmas ascending to the Halemaumau lava lake at the summit had actually already lost their CO2 from the roof zone of a much larger reservoir extending to the east and southeast, reaching the atmosphere through large fractures as diffuse degassing over the caldera floor. Now, the latest piece of the puzzle comes from the most recent eruptive episode, the 2018 Lower East Rift Zone eruption, located a long way down the East Rift Zone, up to 70 kilometres, and erupting more than 1 cubic kilometre of basalt. And here is a map of the flow field from this eruption, published by Neal et al. In Science in 2019. Now, the SO2 fluxes from this eruption were so large that they were best viewed from space. And estimates of SO2 flux measured from the ground using UV spectroscopy were around 50,000 tonnes per day, although using spectroscopic methods for such large mass burdens of SO2 is a real challenge. A prevailing problem at Kilauea and other volcanoes is the VOG, and that's volcanic smog. SO2 reacts with hydroxyl in the presence of UV in a sequence of reactions to form sulfate aerosol in the form of breathable particles. And this is a significant health hazard in Hawaii and elsewhere, and exacerbates asthma and other respiratory conditions. The 2018 eruption produced unprecedented air quality issues in Hawaii, and the gas plume is typically carried to the southwest under the influence of the trade winds and is then blown back on land on the Kona coast on the west. And by this time, a significant proportion of the SO2 has oxidised to sulfate, although this was poorly understood. In 2018, a team from Cambridge, Leeds and Oxford acquired gas and aerosol samples from all over the island to try and map the conversion to sulfate and to quantify the metal composition of the aerosol phase. And they picked up samples from all of these different locations around the island. And we found that concentrations of particulate matter small enough to breathe in exceeded World Health Organization guidelines, particularly on the west coast of Big Island, several times during the 2018 eruption. And I should say that these sites are more than 100 kilometres away from the eruption site. Now, the measurements showed that up to 15 to 20 hours after emission, as the plume is curving back and hitting the west coast, up to 20% of this SO2 has converted to sulfate. So that gives a really nice insight to the reaction rates of the oxidation of SO2 and the formation of VOG. We also found that the emission rates of volatile metals and semi-metals like copper and zinc, lead, arsenic, cadmium and selenium are comparable to the output from entire countries. So the output from Kilauea is shown here in the red column on the left as a daily rate, and the output from entire countries on a similar timescale is shown in grey to black. And these metal aerosols exist as soluble chlorides in the plume, particulate matter, and they're lost by wet deposition much quicker than the more lithophile elements, which are held in fine silicate ash particles, and these persist longer. And you can see the difference in this plot, where the volatile metals are plotted here, normalised in terms of their mass by the source, and here is the approximate plume path length, and you can see that these volatile metal aerosols are depleted much faster than the lithophile elements present in the fine silicate ash. Now, I also want to mention that this eruption has allowed the use of unmanned aerial vehicles to characterise volcanic emissions, and these developments are being driven largely by the USGS and by other groups. And I want to highlight in particular the work of Emma Liu, now based at UCL. We also characterised the composition of the plume that's formed when lava reaches the sea and flows into the sea, and here the seawater is being boiled to dryness when it's heated by lava. And the plume is largely comprised of water, steam, but also concentrated hydrochloric acid formed from seawater salts. But it also contains elements derived from the degassing of lava. And in particular, it's enriched in those elements that speciate with chloride in the plume. And these would be cadmium, zinc, silver, copper, bismuth and rhenium. And these findings could be important for understanding biogeochemical cycling in early Earth environments where lava-seawater interactions were more commonplace. So Kilauea has been a natural laboratory for degassing studies, and its typical behaviour mean that generic models applicable to ocean island volcanoes globally and even on other rocky planets have been built here, and it's been the testbed go-to volcano for new technology. Activity at Kilauea waxes and wanes, and it's paused for the moment, but there's no doubt that it will remain long into the future a critical site for volcanology. Thank you.